Hello, everybody. This is a 15 minutes longer version of the talk, which was given in EGU 2022 at the session Turbulence and Plankton in Vienna. So it's about the Agiturb laboratory turbulence generation system and its application to plankton studies. We are going to show application to zooplankton and phytoplankton. I'm François Schmidt from CNRS LOG, Laboratory of Oceanology and Geosciences in the north of France. And you can see here also the list of my co-authors. So globally, in fact, we know that turbulence play a big role in marine ecosystems. It plays a role for mixing, for transport of particles, transport of different dissolved quantities, and also the contact rate between particles. We have the citation of Amboul in 1959 about the role of turbulence in marine ecosystems. And Margalef in 1997 said there is no life without water and there is no life in water without turbulence. So turbulence is also very important for plankton because plankton lives by a definition in suspension in water. It's fully adapted to its turbulent environment. It belongs to Lagrangian transport. Turbulence plays a big role in the diffusion of oxygen of particles of different quantities, and for zooplankton there is a big role of the contact rate, the transport, and for phytoplankton diffusion of nutrients, also transport, and the relation with light in the euphotic zone. So in fact, for copepods, copepods, they are small crustaceans. We have a lot of species. They are completely adapted to the turbulent environment. And we know that there is something which is called the dome shape, saying that in fact, when you have still water, so no turbulence, it's not optimal. When you have too much turbulence, it's not optimal either. And in the between, you have a kind of optimal turbulence level for the ingestion rate of copepods. So our question is to know is the swimming activity depending on turbulence, and what is the optimal turbulence level for such species. So what we are doing here belongs to the field of geosciences, and to study geosciences, we have three frameworks: theories and models, observation in the field, and also experimentation in the laboratory using well-defined controlled experiments. And this is what we are doing here. So we are doing experiments in the laboratory. We have been inspired by a system which is called Foro Mill, which was proposed by Taylor in 1974, which is a laminar, strain-dominated two-dimensional flow, where you have compression zone and extension. And we have not done exactly the same system, but we have proposed something which is similar. So we have a cubic tank, and we put below it agitators, and we have four steering bars which are activated by magnetic stirrers. They are contra-rotating, and they are situated under the tank. And we call this system Agiturb, and it's an easy system which is able to generate controlled turbulence. We can see here different movies showing the system in action with particles. And on the right, we have the top view. And so we can record using a laboratory velocimeter, the mean velocity in the central zone. And we can plot, which is shown here, the mean velocity versus the rotation rate. Omega is the rotation rate in rotation per minute. We have also other characteristics of the flow. So we have the kinetic energy, which can be computed using the mean velocity. We have the dissipation of kinetic energy, which is built using this mean velocity, and also a scale L. So this scale, capital L, is a distance between two agitators, and it's in fact the injection scale of the system. We can also build the Kolmogorov scale, which is the small scale of turbulence. And below the Kolmogorov scale, you have no more turbulence, and above the Kolmogorov scale, you have the turbulence regime. And we can build also the microscale Reynolds number, R lambda, which is characterizing the flow. So we see on this graph the dissipation rate versus the rotation, omega. And we have dissipation, which is representative of the ocean medium. We go from weak turbulence to coastal zone, surf zone, and storm. And we can do the same for R lambda. Also, our R lambda, the microscale Reynolds number, goes from 130 to 360. And so it's a way here, in fact, to be able to characterize the main properties of the turbulent flow. And usually in the field of turbulence, what we do is we give the kinetic energy K, dissipation epsilon, and the Reynolds number R lambda. And with these different numbers, we have a way to characterize the flow and also to compare different situations and compare what we are doing in the laboratory with field measurements. So the first application was to apply this to copepods. So we use high-speed cameras. We use infrared lamps to avoid the phototropism of copepods. So we are filming in the dark using the infrared lamps. And our high-speed camera are sensitive in the close infrared. And in fact, we estimate the 2D trajectories in a horizontal plane, and we put about 10,000 copepods in the system. So by doing this, we are able to extract trajectories. And so here we have an example of different trajectories which are extracted by the system, and we see the different particles that are moving. So by doing this, we can also do a filtering and to be able to extract also the velocity and the acceleration. And we see on the right a zoom of a jump event with the display of the acceleration versus time. So by doing this, we made different experiments. We made comparison between copepods which were dead and alive in order to see the role of the swimming activities. We also compared copepods with polystyrene particles of the same size. And what we found is that dead copepods and polystyrene particles are very close. They have close properties. And also we looked at the PDF of the velocity. And on the central panel, we see the PDF. So the green curve is the PDF of alive copepods, and the gray one is the PDF of dead copepod. So we see above a given threshold that there is a difference in the PDF, showing that in fact we have swimming activity for this Reynolds number. But for larger Reynolds number on the right panel, we see no more difference in dead and alive copepod, indicating that there are no more swimming. So the interpretation is that, in fact, there's too much turbulence, and the copepods say, okay, it's too agitated for me here, I'm just stopping to swim. So there is a given level of Reynolds number where the copepod is happy to swim. We did the same for acceleration, and we see here the different comparison. On the right, with large Reynolds numbers, there is no difference on the acceleration PDF. In the central panel, in fact, we see differences between alive and dead copepods for the PDF of the acceleration, and on the left panel, the same. So in fact, we have the same phenomenon for acceleration, but the threshold in Reynolds number is a bit larger. So our conclusion, it was our first use of the Agiturb system, which is published in the reference which is given here. And what we found is that, in fact, we have a dome effect. Also, we have an optimal window of turbulence for copepod swimming behavior, but we don't find the same threshold in Reynolds numbers for velocity and for acceleration in the copepod behavior. We have also applied this in another project, which is called Turbulence, and which is a way to look at the effect of turbulence on proliferation and also toxicity of diatoms. We have chosen pseudo-niche diatoms. It's diatoms that can produce toxin, such as domoic acid. and it belongs to harmful algal bloom species. So in the literature, this species has been found in the Eastern English Channel. And also what has been found is that the fact that the morphology and also the gene expression in diatoms may depend on turbulence. And this is what we wanted to check in this project. So we have performed a culture of different species of Pseudonychia under controlled conditions, so 15 degrees, 32 PSU, and there is also an alternation of dark and light conditions. We have used 9 tanks, so it was 6 Agiturb tanks with agitators and 3 control tanks without turbulence. And so we have done experiments with a given level of, with different levels of turbulence. So in fact, there were 2 weeks of experiments. The first week, it's experiment 1. We have control and calm and agitated turbulence level. So it's 200 and 400 RPM. And experiment 2 on week 2 was control and weak turbulence with RPM of 100 and strong turbulence with RPM of 900. And what we have done also is to make sampling in the systems at t equals 0, so in the beginning, so about after 1 day, after 2 days, after 3 days. And different quantities have been measured: the growth, the chain length, pigment, toxin, metatransnomic, nutrient, pH, bacteria, virus. So we see here, in fact, a movie showing the system in action. And this movie shows, in fact, that depending on the level of turbulence, just by visual inspection, we can see that some tanks have a very high level of cells. So what we are doing here is the first study. So the first one was looking at the growth rate. So for this, we have looked, because the growth rate is supposed to be exponential. So we have looked at the abundance versus time in a log linear plot. And from this, we are able to extract the growth rate. And what we find here is a slight dome shape effect. So with no turbulence and low turbulence effect, we have more or less the same growth rate. There is an optimal for a given Reynolds number, which is a medium level. And when we have very large turbulence level, like corresponding to a storm in the system, in fact, the growth rate is lower than without turbulence. We have also looked at the chain length, because this is a species that can form chains. We see here different pictures. On the right, we have a picture with a chain of 4 cells. And the methodology was to count, in fact, for samples, the chain length. We have, in fact, considered 3 classes. So isolated cells, so only a chain of only 1 cell, short chains with 2 or 3 cells, and also long chains with more than 4 cells. We have looked at the percentage, so it means in fact the percentage of each class, and we consider the time dynamics of this percentage, and also we compare the percentage at a given time for different Reynolds numbers. So this is the chain dynamics. So we are plotting, in fact, the percentage versus the time. And horizontally, it's the time. Vertically, it's the percentage. So on the left, it's the percentage of isolated chains. In the middle, percentage of short chains. And on the right, percentage of long chains. And what you can see is that, in fact, for a given Reynolds number, so for isolated cells, we see that for each turbulence level, we have a minimum after 1 day, and then we have an increase of the percentage. And this minimum is the smallest for R lambda, which is equal to 160. And for short chains, we have a maximum of the percentage. between 1 and 2 days, and the maximum is larger for R lambda equal 240. And for long chains, in fact, we have a rate which is large only for 3 turbulence level between 160 and 240. And we have a pike after 1 day. And we can also look at what is happening versus Reynolds number. So what is interesting in the panel in the center, we are considering short chains, and we see in fact that we have also a dome effect, and we have an optimal turbulence level, which is between 130 and 240. And this optimal turbulence level is found also between 1 and 2 days. For long chains, we have also an optimal, but the window is much narrower, and which is close. We have a pike for R lambda equal 160. And what we find also is, in fact, this pike has a duration of only 1 day. So globally, what we can say from this is that, in fact, we have a new system, Agiturb system, which is cheap. So the order of the cost is €1,000. It's able to generate controlled turbulence in the laboratory. We can also characterize different quantities to quantify turbulence, like the dissipation rate and also the microscale Reynolds number. And these correspond to values which are found in the field. And we also considered 2 experiments, one with copepods, one with diatoms. We found optimal levels of turbulence, showing a kind of dome effect. A dome effect first for the swimming behavior, and then for the growth rate of diatoms, and also for the chain formation. And in each case, in fact, the optimal values were between R lambda of 160 to 240. Depending on the different applications. So we acknowledge financial support of the project which are listed here. And I finish with 2 books of mine which were published recently, one in English and one in French. Thank you very much for your attention.